हा. मी लाईव्ह लिंक शेअर करतोय मॅडम आणि त्यांना सांगतो की शार्प 10:30 ला स्टार्ट होईल. हॅलो, बाकीचे आहेत, मला कोणी रिस्पॉन्स करेल? मी लाईव्ह लिंक शेअर करू का म्हणून? हॅलो, प्राजक्ता मॅडम, वृषाली मॅडम. हॅलो
हॅलो, हा बोला.
लाईव्ह लिंक चालू झाली मॅडम, मी शेअर करू का? म्हणजे मी माझं ट्रायल ओके.
शेअर करा आणि
लिंक
बोलू
शेअर
नका
करतो
जास्त.
आणि खाली मेसेज टाकतो की शार्प 10:30 ला चालू होईल म्हणून.
हो चालेल.
ओके ओके, शेअर करतोय हा मॅडम.
हा हा.
ओके,
आणि
ऑल द
तुम्ही
बेस्ट.
ते बॅकग्राऊंड आवाज ऑफ करता का नाही करता?
नाही, वापस आहे ना, कालची सेटिंग करून ठेवली ती वापस आहे.
बॅकग्राऊंड व्हॉइस
3
ना
जण व्ह्यू
ऑफ,
झाले आपले आता.
बॅकग्राऊंड व्हॉइस आहे ना
बॅकग्राऊंड
ऑफ
वापस आहे.
करत जा सर.
फक्त मी हे जे बोलतोय ना ते मी लॅपटॉप जवळ बसूनच आहे म्हणून याचा आवाज कदाचित रेकॉर्ड होईल फक्त. आता हे शेवटचं आहे, अजून कोणाला शेअर केलं नाही म्हणून, बाकी काही नाही.
बरं चालेल. हा करा.
एकदा शेअर केली की मग आपलं चालू होऊन जाईल, कोणाच
हा
कोणाशी
हा
बोलणार नाही.
चालेल चालेल.
आणि काही प्रॉब्लेम आला तर मी तुम्हाला टाईप करून सांगेल किंवा दूर बोलून तरी मिनिमम सांगेल.
चालेल.
ओके, लाईव्ह लिंक शेअर करतोय.
हा हा चालेल.
ऑल द बेस्ट.
हा.
ओके ओके. प्राजक्ता मॅडम, लाईव्ह शेअर केली मी, कनेक्ट करा आणि प्रॉपर आहे का बघून घ्या एकदा आणि मला फायनल मेसेज द्या की ओके सर म्हणून. माझ्या ट्रायल मध्ये ओके आहे, पण तुमच्याकडून पण कन्फर्मेशन हवं.
हॅलो, हा सर, माझा आवाज येतोय
ओके
का
ना मॅडम?
युट्यूबला?
येस येस येस, येतोय येतोय येतोय.
स्पष्ट येतोय ऐकायला?
हो, येस येस, स्पष्ट आहे.
Hello, am I audible to everyone?
Yes, madam.
Good morning, everyone. It is my pleasure to extend a warm welcome to all of you on behalf of Shivaji Rao S. Zondare College of Pharmacy, Asangaon. On the fifth means last day of our FDP session, I requesting to Professor Manjusha Sanap ma'am, please give keynotes for today's first session.
Thank you, Rushali, ma'am. I'm very glad to welcome our today's resource person, Miss Prajakta Subramani madam and Dr. Lalit Sonone sir. So first session is conducted by Professor Prajakta Subramani madam. So I welcome madam. So as a resource person for today's session, Miss Prajakta Subramani madam work as an assistant professor in Shivajirao S. Zundare College of Pharmacy, Asangaon. She is having total 6 years of experience in academic. She completed her B Pharm and M Pharm from Bharati Vidyapit College of Pharmacy, Asangaon with first class. She attended total 7 national and international conferences. She published 3 papers in national and international journal. She completed implant training from Okhad, Aurangabad. Her area of interest in drug design and development, quality assurance, and research and development. So now I request Prajakta madam to conduct her session. Thank you. Excellent.
सर स्क्रीन है जी मीट पर वॉइस कॉल कर
Chaudhary sir. Chaudhary sir, you there?
I request Prajakta madam to continue your session.
Thank you, Manjusha ma'am. Good morning, all of you present over here. I am Ms. Prajakta Subramani, Assistant Professor, Shivajirao S. Zondhe College of Pharmacy, Asangaon, from the Department of Pharmaceutical Chemistry. So, this is the 5th day of our online FDP on spectroscopic methods for techniques for pharmaceuticals. In that, I am going to take in general instrumentation about infrared spectroscopy. These are the contents. So we are going to discuss about types of vibrations, principles, instrumentation, applications, and limitations. So as we know that infrared or vibrational spectroscopy is the study of absorption of IR radiations results into vibrational transitions. So spectroscopy involves the study of interaction of the electromagnetic light with the matter. So what type of light is interacting? Accordingly, we categorize the spectroscopic methods. Before means in FDP, in the before 4 days, we have learned so many of chromatographic techniques, so many spectroscopic techniques. Okay, so we already have know that when the UV or visible light interact with the matter, it constitutes the UV or visible spectroscopy. In the same manner, when IR light strikes to the sample, we observe the absorption of IR light and observe the changes taking place in the molecule and constitutes the IR spectra. Before going into deep, have a look upon the IR spectrum. So what is the region of IR? So IR spectrum is consist of the gamma rays, X-rays, UV rays, visible light, and IR light, microwave light, and radio waves. So on the right hand side towards the gamma rays, as the wavelength is get smaller or decreases, energy get increases. And on the left hand side, as the wavelength get increases, energy get decreases, as well as frequency get decreases. So we can conclude that wavelength is inversely proportional to the frequency or the wave number. So IR light has wavelength 10 raised to minus 5. Further, IR light is subdivided into 3 regions. We are going into deep later. So the energy required to excite the bonds between belonging the molecule and to make them vibrate, the presence of separate areas of partial positive and negative charge is the vibrational energy. The change in the vibrational energy leads to another corresponding change in the dipole moment of the given molecule. So let's see the principle. The principle of IR spectroscopy is related to the vibrational and rotational energy of the molecule. When the frequency of IR radiation is equal to the natural frequency of vibration, then molecule absorbs IR radiation. Absorption of IR radiation causes an excitation of molecules from lower to the higher vibrational level. The IR spectroscopy theory utilizes the concept that molecule tends to absorb specific frequencies of light that are characteristics of the corresponding structure of molecules. The energies are reliant on the shape of molecular surfaces, the associated vibronic coupling, and the mass corresponding to the atoms. So, in IR, so all the bonds in the molecule are not capable of absorbing IR energy, but those bonds which are accompanied by a change in dipole moment will absorb the IR region, and such transmissions are called as IR active transition molecule. For instance, the molecule can absorb the energy contained in the incident light and the result in a faster rotation or a more pronounced vibration. So in IR spectroscopy, the changes in the vibrational energies depend upon mass of atom present in the molecule, then strength of the bonds. That means it is a polar bond or covalent bond or ionic bond or delocalized electron bond or the bond which can be shared, okay, pi bond, sigma bond. Now, and third one is arrangement of atoms within the molecule. When IR radiation interact with sample molecule, the sample molecule will absorb the specific applied quantized IR light, which is matched with the internal vibrational frequency of the molecule, and other residual frequencies are transmitted via sample. Due to absorption of IR radiation, the net change of dipole moment in the molecule is occurred and causes vibration of bonds in the molecule like stretching and bending vibration. The transmitted light is detected by the detector and IR spectrum is interpreted on the computer screen by analysis of the transmitted light. So moving towards IR regions. So there are three regions: near IR, mid IR, and far IR. So near IR, it measures wavelength 0.8 to 2.5 micrometer, while it's having wave numbers 12,500 to 4,000 centimeter inverse. So these are interfered with UV radiation and gives extra IVCT, means intervalence change transfer bands on the IR spectra due to delocalization of electrons. Now mid-IR, it measures wavelength 2.5 to 5 micrometer and wave number 4000 to 200 centimeter inverse. So the mid infrared region is appropriate for the IR spectroscopy because it gives fully IR peak. Okay. Now far IR, it wavelength measures 50 to 1000 micrometer. Now see how the wavelength is increases and wave number is decreases. So wavelength is inversely proportional to the wave number, and wave number is smaller in far IR, that is 200 to 10 centimeter inverse. Far IR is also closer to the radio waves region and sometimes bandly interact and formed extra unwanted band spectra on the IR spectrum. So VR generally uses mid IR region. Now next is molecular vibrations. Okay, so there are two types of vibrations: fundamental and non-fundamental vibrations. So in the fundamental vibrations, stretching and bending vibrations, while stretching is having symmetric and asymmetric types, which is having higher frequency, and bending vibration is having lower frequency, and again divided into two parts: in plane and out plane bending. While in plane bending is of two types: scissoring and rocking. We will go into deep in the next slide. And out plane bending again classified into two parts: twisting and wagging. Okay, the bending vibration is usually more than the number of stretching vibrations in IR spectrum. Okay, now stretching vibration. It involves a continuous change in interatomic distance along the axis of bond between two atoms. In symmetric stretching, the bond length increases and decreases symmetrically. In asymmetric stretching, length of one bond increases and another one decreases at the same time without changing bond angle. So we will take example of here is non-linear triatomic molecule of water. So water is a non-linear molecule since the two hydrogen atoms are linked to the oxygen via only one molecular bond each. So it follows the two hydrogens which are not in line with each other gives rise to a permanent dipole moment with the molecule. Okay, so one symmetric stretching, one asymmetric stretching, and one scissoring vibrational mode of vibration is takes place in the water molecule, and the scissoring vibrational mode gives rise to an absorption peak at 1595 centimeter inverse. Okay, why scissoring is occur here? Because of dipole moment, and dipole moment occurs because of force of attraction between two hydrogen, as we know that hydrogen bonding. Okay, now next is bending vibrations. This involves change of angle between two atoms. So scissoring, it is the movement of two atoms towards and away from each other. Rocking, it is the bond angle maintained, in which bond angle is maintained, but bond moves within the same plane. Okay. Wagging, in which both atoms move one side of the plane and changing angle to the plane of the group of atoms, and twisting in which one atom is above the plane and other is below the plane. Okay, so I'm going to take an example here. Example of linear triatomic molecule of CO2. H2O was non-linear. Okay, and linear is CO2, carbon dioxide. So carbon dioxide only exhibits two absorption peaks at 667 and 2360 centimeter inverse. The reason for this discrepancy is as follows: that there are two stretching vibrations that can occur. One of these is symmetric, whereas one other is asymmetric. Okay, so it is only the asymmetric stretching, however, that changes the dipole moment of the molecule, where the force is capable of giving rise to an absorption peak at 2360 centimeter inverse. Two scissoring vibrational modes are also possible. However, these are energetically equivalent to each other. So they said to be a degenerate. So now, modes of molecule with respect to electromagnetic radiations. So now, which type of modes are there? If molecule get in energy, so it get excited and it gives three modes of electromagnetic radiation. So these are rotational, translational, and vibrationals. So before going into depth, so first of all, we should know that what is degree of freedom. So it is the total number of variables used to define the motion of molecule completely. For n atoms, any n number of atoms, the molecule moving in 3D space, there are three n motions like moving, rotation, and vibrations. Okay, so now the total number of degrees of freedom can be given: translation energy translation plus rotational plus vibrational into degree of freedom. So for linear molecule, vibrational degrees of freedom can be given as 3n minus 5. For non-linear molecule, vibrational degree of freedom is given as 3n minus 6. Now, what is IR spectrum? So IR spectrum is the graphical plot of transmittance versus vibrational frequencies. So by historical convention, IR spectra are normally displayed in somewhat different manner to UV visible spectra. The Y scale of an IR spectrum is normally plotted in terms of percentage transmittance instead of absorbance. This means in practice that the baseline of spectra lie towards the top of spectrum or the maximal transmittance, and IR absorption peaks are directed down to the page. So you will see also the X scaling is not displayed in terms of either wavelength or frequency, but rather wave numbers. Wave numbers represent the reciprocal of wavelength, 1 upon wavelength. So, and have units of centimeter inverse. The use of wave number rather than the wavelengths owes its original to historical convention, but allows for the use of rather more manageable numbers. It should be noted that increasing wave numbers correspond to increasing frequency and therefore to progressively more energetic radiations. So here IR spectrum having two regions, okay, that near, mid, and far region, this is different. But when we are going to find out molecular formula from the specific molecule or a specific drug, so we divided the region as functional group region and fingerprint region. So functional group region is having 4000 to 1500 centimeter inverse wavelength wave number, and fingerprint region measures 1500 to 500 centimeter inverse wave number. So functional group region identifies the functional groups with consequence of changing stretching vibrations. And the pattern of peaks is very easy to analyze because stretching vary within a narrow range, and it will give sharp, broad, strong, and medium peaks. Okay, in case of functional group region. In case of fingerprint region, it identifies the exact molecule with the consequence of changing bending vibration, and the patterns of peaks is more complicated due to complex vibration which create a unique IR band to distinguished compound, and it gives sharp and weak peaks. So here is the formula. Transmittance is given as intensity of transmitted light to the intensity of incident light. Okay. Nu bar. It is given as a 1 upon wavelength, means wave number is given, wave number is inversely proportional to the wavelength. So which are the different factors affecting vibrational frequencies of the functional groups? So first one is effect of different mode of vibration. Okay, so frequency of stretching is higher than the bending mode. Second one is reduced mass of atoms, which is inversely proportional to the vibrational frequency, and it is given by the nu bar is equal to 1 upon 2 pi c into under root k upon mu. So where v bar is frequency in centimeter inverse, that is, or nu bar, sorry, c is velocity of light, which will be constant, k is the force constant in dynes per centimeter, m is the atomic masses, and mu is the reduced mass. Okay. Third one, electronic effect. Conjugation or resonance is directly proportional to the vibrational frequency. Means for there is an example of aniline. Aniline has 5 resonating structure because of continuous delocalization of electron as well as the pi electrons present on the nitrogen. Okay, so conjugation is also here, resonance is also here, so vibrational frequency of aniline is also more. Okay. Fourth one is hydrogen bonding effect is inversely proportional to the vibrational frequency. Next is multiplicity of bond. So number of bonds are directly proportional to vibrational frequency. Means if a single bond is there, vibrational frequency will be lower. Double bonds will be there, then vibrational frequency will be more than single bond. Okay, like that. Now next is nature of hybridization. In that, percentage of S character, which is directly proportional to the bond strength. Now percent of S character means if you are seeing the molecule having polar carbon, that is polar CH3 group, which ends the suppose a molecule ends with the CH3 group, the S character of that carbon, and in the if you say the mid carbon, which is having S character lower, because it can be contain triple bond or double bond or maybe attached to oxygen, nitrogen, sulfur. Okay, any rather than any carbon atom. So the S character of that carbon is different than the S character of carbon of the polar group. So the S character is directly proportional to the bond strength. Okay, because that polar carbon which is attached to the 3 hydrogen, that bond strength will be different. And the mid carbon, for example, we are taking 2 butene. Okay, 2 butene. So that second and third number of carbon possesses different S character because they are attached to only 1 hydrogens, and they are having 2 double bond between 2 carbons. Okay, so bond strength is different, and that the 2 polar carbon, they contain S character different, which is inversely proportional to the bond length and which is directly proportional to directly vibrational frequency. So fewer peaks are observed when the symmetry of molecule is such that number of change in the dipole moment occurs via 1 or more possible molecular oscillations. If molecule can exhibit 2 or more differing vibrations that are nearly identical to each other in energy, then IR absorption peaks for these processes can sometimes merge and appear to be 1. If a molecular vibration gives rise to an extremely small absorption, then in some instances it may be too small to be detected. Okay. The absorption of peak may not be monitored if it is either outside the wave number range becoming monitored or beyond the range of the instrument. Okay. So these are some conditions. Okay. So here are two formulas for calculation of vibrational frequency as we have seen in the previous slide. So here mu bar is equal to 1 upon 2 pi c into under root k upon mu. As larger the k, higher will be the frequency. Okay, larger is the force constant, higher will be the frequency. Larger is the atomic masses, lower will be the frequency. Mu is what given? Reduced masses. So reduced masses, if larger the atomic masses, lower will be the frequency. And pi is the constant. So how the k is increasing order? Okay, so look at the molecules. Alkynes, it is having 2150 cm inverse, which is more than alkenes and which is more than alkanes. Okay, so increasing force constant as the increase in bonds or the strength of the bond, and increasing mu means increasing reduced mass. For example, CH, it gives 3000 centimeter inverse, which is more than CC, which is more than CO, which is more than CCl. Okay. Now, how to interpret or analyze IR spectra? So, in previous lectures, so the top faculties or the top professors and principals have been explained very nicely that how to interpret or analyze IR spectra. I don't know Dr. Marathe sir is there or not, but he has taken very nicely that. So I'm not going that much of depth. IR spectra isn't generally used to determine the whole structure of an unknown molecule, but IR spectra is great for identifying certain specific groups. Hence, here an overview of the IR window from 4000 to 500 centimeter inverse, that is a functional group regions. Various region of interest, these are highlighted. So here OH stretch is 32002, 3400 centimeter inverse. I'm highlighting only those atoms which are generally used in our drug synthesis. NH stretching is 33002, 3500 centimeter inverse. CH stretching is 2850 to 3100 centimeter inverse. Okay. In case of alkynes, it is different. In case of alkyl, normal alkyl group, it is different. Okay. In case of cyanide, it is different, and in case of alkyne it is also different, because carbon is bonded with three bond to the nitrogen, and carbon is bonded with carbon with a 3 bond, but spectra is different because of dipole moment, okay, or because of electronegativity or because of mass, as I explained before. So, and even more compassed overview. So pick takes place between zone 1. Zone 1 is given as a common symbol bond is X bond H, where here X will be the oxygen or carbon or nitrogen. Here X is not halogen. Okay, remember this, X is not for halogen. It is giving oxygen, carbon or nitrogen. It represents these molecules. Okay, so for example, OH bond, CH bond, NH bond, it is given as a third 3600 to 2700 centimeter inverse. See the diagram number 1. Alcohol, in case of alcohol, OH bonding. Okay, so like that, different zones are there. So OH bond stretching is at 3650 to 3200 centimeter inverse with strong intensity. Okay, and broad U shaped. Okay, we can see there. Now terminal alkynes stretching at 3340 to 3250 centimeter inverse with a stronger and sharper peak. Why? Because they are terminal. If it is middle alkyne, then stretching will be different. Okay, why? Because of S character. Because of S character of carbon, it changes terminal middle. Okay. Now, what are the conditions or criteria to absorb IR radiations? When applied infrared frequency in equal to natural frequency of vibration, then the absorption takes place and peak is observed. Only molecule gives absorption, IR absorption. Molecules must have a dipole moment. The mode of vibration of the molecule should not be center of symmetry, and the molecule should be polar. Okay, can I talk in Hindi? अभी molecule polar क्यों होना चाहिए? So we synthesize drugs. Okay, we are administered them orally. Okay, so what happens? Pharmacodynamic and pharmacokinetic actions are takes place when we administer one drug. So हम टैबलेट किससे लेते हैं? पानी से लेते हैं. सो वो वाटर इज पोलर, सो पानी में वो डिसॉल्व होना चाहिए ड्रग. अगर आप ऑयल लेंगे तो ऑयल नहीं डिसॉल्व होगा, और ऑयल की टैबलेट कैसे बनेगी? उसके लिए वो नॉन पोलर ग्रुप के लिए पोलर ग्रुप तो चाहिए, और डाइपोल मूवमेंट किसके लिए चाहिए? व्हेन वी एडमिनिस्टर दैट फार्माकोकाइनेटिक पैरामीटर के लिए तो पोलर ग्रुप चाहिए ही चाहिए, बिकॉज it should be dissolved in our HCl of stomach. It should be dissolved in our intestine where buffer pH is there. Okay, it should be excreted through our kidney. Okay, where the so ionization should takes place of drug for metabolism. So drug तो polar तो होना चाहिए. ये हो गया pharmacokinetic. Now pharmacodynamic. Why drug should be polar pharmacodynamically? Because our body is made up of carbon and hydrogen. Okay, our skin is oily in nature, but when we apply drug on the skin, for example, there are some skin lotions. Okay, we apply on the skin. They absorb through our body. Why they absorb? Because there is polar as well as non-polar part. Our amino acid, our body is made up of amino acid. Amino acid also contains polar and non-polar part. Okay, now main point is what? Our receptors where our drug has to go and give the biological effect after attachment. So वो कब इफेक्ट देगा हमारा ड्रग? जब वो रिसेप्टर को जाके बाइंड होगा. रिसेप्टर को जाके कब बाइंड होगा? ऑयल होगा तो वहां पे ऑक्सीजन अटैच होगा क्या? नाइट्रोजन अटैच होगा क्या? Receptor is slightly oily in nature as well as means slightly non-polar in nature as well as slightly polar in nature. Okay, so our drug should be like that. It should be pitched to the receptor. It should be interactive to the receptor, because the receptor also containing amino acids, because they are made up of proteins. They have NH2 group, they have polar as well as non-polar group, COH group. Our drug must contain polar group, so that our drug must contain dipole moment, and dipole moment होगा तभी IR प्रेडिक्ट होगा. अगर आपने कुछ सिंथेसाइज किया है और अगर उसका IR ही नहीं आ रहा है तो वो खाने के लायक नहीं है. वो आप आप उसको ड्रग बोल ही नहीं सकते हो. So this is instrumentation, IR spectroscopy instrumentation. This is in general IR spectroscopy instrumentation, and next diagram is FTIR, Fourier transfer IR instrumentation. So okay, so the steps in the IR spectroscopy. Radiation, first we should have radiation sources for striking the light to the molecule. Then monochromators for splitting of the light. Particular wavelength की light हमको मिलनी चाहिए. then sample cells and sampling of substances, detectors and recorders. So first, a beam of IR light from the source is split into two and passed through the reference and the sample respectively. Now both of these beams are reflected to pass through the splitter and then through a detector. Okay, final here is the splitters are there. Okay, source, then reference sample, reference and the sample. Okay, and here is a attenuator. Okay, where the splitter is there. Finally, the required reading is printed out after the processor deciphers the data passed through the detector. Okay. Now, first one is the IR radiation sources. You are seeing two diagrams. So one is mercury arc. That first one is mercury arc, and second diagram is it is tungsten lamp. So IR instrument require a source of radiant energy which emits IR radiation, which must be steady, intense enough for detection and extend over the desired wavelength. So various sources of IR radiations we can use nose to blower. The nurse blower source comprises thin cylindrical fabricated from rare earth oxides and approximately 20 millimeter in length and 1 to 2 millimeter in diameter, and current is passed through the cylinder for heating via electrical connections and at either end. Okay. So IR sources comprises an inert solid that is electrically heated to a temperature in excess of 1500 degrees Celsius. The radiation emitted at this temperature approximates to that of black body, although the intensity of radiation is not uniform across all frequencies of IR range. How it can be same? A maximum intensity of the emitted radiation occurs at frequencies equivalent to approximately 5000 to 6000 centimeter inverse, with the intensity of emitted radiation falling away either side of these limits, although this is most pronounced as shorter rather than longer wavelength. Then incandescent wire IR sources. The incandescent wire as IR source formed from the tightly wound and electrically heated spiral wire. It offers a greater than many other sources, although it cannot provide the same intensity as the nursed or global alternatives. Mercury arc IR sources. It is a high pressure mercury arc sources which are used for far IR applications where the intensity of radiation provided via alternatives such as nursed global and incandescent sources diminishes to unacceptability low levels. The mercury arc sources consist of a quartz jacketed tube containing mercury at a pressure greater than 1 atmosphere, through which current is passed to form an internal plasma that emits IR radiation in the far IR region. Now, tungsten filament source. It is conventional lamps that can be used as IR sources for the near region. Okay, near IR region, and it ranges from approximately 12,500 to 12,500 to 4,000 centimeter inverse. Glauber source. The glauber is an electrically heated silicon carbide rod of around 5 centimeter length and 4 millimeter in diameter. The glauber source typically provides a more intense source of IR radiation than the nursed glauber, and wave number is wave number bears 2000 centimeter inverse. So this is about IR radiation sources. So next one is the monochromators. So monochromators, various types of monochromators are prism, gratings, and filters. Prisms are made up of potassium bromide, sodium chlorides, or cesium iodide. Filters are made up of lithium fluoride, and diffraction gratings are made up of alkali halides. Now, sample cells and sampling of substances. IR spectroscopy has been used for the characterization of solid, liquid, or gas samples. So, in case of solid, a thin film of solid of some polymeric samples like polystyrene or polyethylene may be placed in the path of IR beam directly, and IR transmission analysis can be done. And the most widely used approach for the determination of IR spectra is to determine protein structures. So, how it can be done? Sampling. The okay. So, solid samples may be obtained by either dissolving the solid in suitable solvent or preparing slurry or mull or using an attenuated internal reflectance technique. Okay. So, solid sample of materials such as leather or paper may be analyzed directly by ATR techniques by placing the sample in direct contact with ATR crystals. Okay. So, ATR means attenuated total reflection. Many liquids and solutions ranging from environmental water through the biological samples, for example, blood, it can be also analyzed by ATR approaches. Now, preparation of mulls for dispersive IR analysis. Uh, Liquid samples can be held using a liquid sample cell made up of alkali halides. Okay, aqueous solvents cannot be used as they will dissolve alkali halides. Only organic solvents like chloroform or carbon tetrachloride they can be used. The technique requires mixing of a ground sample of solid with an inert liquid to form a slurry or mull. And the most popular liquid used for the preparing mulls is nuzol or a heavy hydrocarbon oil. Another liquid, fluoroform, is sometimes used as an alternative. Water is not suitable for the preparation of mull because it displays strong IR absorption and it is insufficiently viscous to hold the salt plates together because the NaCl discs are used. So if we used water, so NaCl discs get dissolved. So after preparation of mull, the small sample is smeared on one pair of NaCl disc, and the second disc is generally placed on the first and they are subsequently held together by the surface tension or capillary action. Okay. Then the two salt disc holding the sample mull is placed then placed within the path of the IR beam to allow absorption measurement for the to directly performance. The preparation of mull and the use of salt disc do not allow the reproducible absorbances to be determined since the mull thin film thickness is clearly extremely variable. And the gas sampling. So dedicated gas handling cells may be used to obtain infrared spectra of gaseous sample, and it is similar to that of sampling of liquids. Now detectors. So detectors are used to measure the intensity of unabsorbed infrared radiations. So there are three main classes of IR detectors, and these are generally classified as operating via thermal, pyroelectric, or photoconducting principles. Photometers and dispersive spectrometers typically employed either thermal and pyroelectric detectors, whereas Fourier transform instruments typically employ either pyroelectric or photoconducting detectors. So here the first diagram is showing pyroelectric detectors, where cap with broadband window is there, stack of 8 pyroelectric elements and IR filters are there, and detector base is there. And the second image indicates the thermal detectors. Okay. So thermal detectors operate via monitoring the heating effects of IR radiation upon a component that is designed to act as a black body. The materials are chosen with very low heat capacities in order to maximize temperature changes upon irradiation with IR radiation. Under the most favorable condition, thermal detectors can respond to changes of few thousands of kelvins. Thermal detectors are normally shielded from ambient thermal radiation to help minimize signal drift and noise effect. Thermocouples are the most popular types of thermal detector, and the simplest thermocouples comprise a length of metal such as antimony, to which two pieces of dissimilar metals such as bismuth, okay, antimony and bismuth, they are attached, and the potential differences develops between the two junction upon heating, and this can be related to change in the temperature between two metal at the junction upon heating of one of the junction. Then pyroelectric detectors. So these are insulators that are polarizable upon applying electric field across opposing phases, with the degree of polarization being independent on the dielectric constant of the material, which is itself function of temperature. Pyroelectric detectors typically comprise a layer of pyroelectric material sandwiched between two electrodes, okay, one of which is made up of IR transparent material to form a capacitor. IR radiation passing through the transparent windows causes heating of the pyroelectric material, and this gives rise to changes in the polarization of the material. So capacitance of the, so we can get the capacitance of detector. So here is the IR spectrum of acetaminophen, that is paracetamol. Paracetamol structure contains one benzene ring, one COOH and NH2 group. So there are different bands. The sharp peak is between near about 16000 to 800 centimeter inverse wave numbers. Okay, so the strong peak which is found is 3400 to 3200 centimeter inverse, where it is OH or NH is present. Now moderate peak suggesting unsaturated CH. So unsaturated CH is from that delocalization of electrons in the benzene ring. Now weak peak indicates at 2900 centimeter inverse, which indicates saturated CH. Okay. Then saturated CH is CO from the COOH. Then no unsymmetrical triple bonds is there, which is showing at 200 centimeter inverse wave number. Then strong carbonyl absorbance is taken place at 1690 centimeter inverse. Okay, now that strong carbonyl absorbance is from COOH. Okay, so it is different than different ketonic group or aldehyde group or ester group. Okay, depend upon the S character of carbon. Also depend upon the mass or the reduced mass mu. Now fingerprint region. The region between 140 and 900 centimeter inverse is a complex region that includes fundamental stretching as well as frequency, sum and difference, such that this part of an analyte has characteristic peak in sample. For example, two similar molecules may have the same fundamental region but have marked difference in the particular region. Therefore, it is called as fingerprint region. So here you can see the fingerprint region of main focus region is for functional group, okay, OH stretch and saturated CC. It is observed in between 3200 to 28 or 2900, and OH stretch is observing at 3400 to 3300 centimeter inverse. So matching a spectrum by eye with the spectra of known compound would be highly tedious. Even if a narrow list of compounds could be shortlisted via examination of the group frequency region of the spectrum. However, many modern ion spectrometers greatly simplify the matching of spectra via computerized data libraries. In this way, the matching of multiple peaks across both the frequency group and fingerprint regions of the spectrum can be performed extremely rapidly. So, with the software, often selecting 2 or 3 of the closest matches with the spectra from its databases. So, this matching software can prove especially useful since analyte samples rarely contain one pure compound but more frequent contain a host of different compounds or impurities of many of which of course we can contribute to and so further complicate the IR spectra. The small changes in the molecular structure often given rise to significant change in the absorption peaks within the fingerprint region, and in this way spectra of unknown sample can often be matched with those of known compounds. So now factors affecting the IR spectrum. Fermi resonance. When two vibrational bands are so close that they overlap where only one band is expected, they are said to be in phase. So the phenomena of doublet formation is called as Fermi resonance. So this effect occurs when an overtone or combination band has a frequency that is similar to the fundamental bands. Coupling. Coupling is very common in molecules with the adjacent bonds of similar frequency. For example, an IR spectrum of molecule containing Cc and Cn may experience this phenomena. So coupling of two vibrational modes, although this requires a common bond to exist between the vibrating groups if this is to be significant. Little or no coupling occurring between two groups due to separation by 2 or more bond length. Then vibrational coupling, and this tends to be strongest when there is an atom common to the two vibrational moieties. Coupling occurs between a bending vibration and a stretching vibration if the stretching bond forms one side of the angle that alters during the bending motion. And this condition happens in SN1 SN2 reaction. We have studied SN1 SN2 reactions. So attack of bromine from backside and from front side. Okay, when bulky groups are there, when isobutane is there, then attack will be done backside from the backside. So bending of that molecule takes place and the bond angle will be changed. And in case of SN2 reaction, only there is a methyl bromide. Only 3 hydrogens are there, which is having low molecular weight, or and bromine can attack directly from frontal side. Okay, so these cases happen. In this case, this happen. And increase in coupling when moieties have individual energies that are almost equally in energy to each other. And for coupling to occur, vibrations must be of the same class of symmetry as defined by the group theory. Now overtones, the vibration that arises from the excitation of the ground state to the first excited state are fundamental absorption, but in some cases these vibrations are complicated by the other vibrations such as excitation of zero state to the second and third state. The states called overtones, for example, the fingerprint region of the IR spectrum at 500 centimeter inverse, the main peak accompanies low intensity peaks. Okay, moving towards the application of IR spectroscopy. So applications are identification of an organic compounds like our drug, proteins, maybe anything, any organic compounds. Structure determinations, then identification of functional groups, then studying the progress of reaction, then distinction between 2 types of hydrogen bonding. Now the studying progress of reaction means if हमको एक प्रोडक्ट बनाना है और उसको 4 स्टेप्स हैं. Okay, so there are some like pamaquine, primaquine. These are like anti-protozoal or anti-malarial drugs. So they have 4 steps. Okay, so we have to check it that the compound or the intermediates are synthesized properly or not, or which group we want there, amine is there or nitro we want there, or oxidation is done properly or reduction is done properly at the which carbon. मतलब हमको अगर 7 पे OH चाहिए, 8 पे अमाइन चाहिए, तो वहां पे वो 8 कार्बन पे अमाइन आ गया है क्या, वो हमको देखने के लिए. ओके, सो ये प्रोग्रेसिव स्टडी करने के लिए दिस इज एप्लीकेबल. Distinction between 2 types of hydrogen bonding. Then study of ketoenol tautomerism. Then study of cis trans isomerization. Conformation analysis. Determination of impurities in compound and presence of water in sample. So these are some applications. Okay, now presence of water in sample. This is utilized by the industrial purpose because अगर आपकी ड्रग में API में वाटर रहा तो मॉइस्चर पकड़ेगा और वो डिग्रेड हो जाएगा जल्दी से, या फिर बैक्टीरियल ग्रोथ हो सकती है, इसलिए वो FTIR थ्रू API चेक करते हैं. Now limitations of IR spectroscopy. It can't determine the molecular weight of the compound. Okay. Doesn't give information about the relative position of different functional group in the molecule. Position नहीं बताएगा आपको वो कि 7 पे है अटैच है ये NH2 ग्रुप, या 6 पे अटैच है, या डबल बॉन्ड इधर है. From the single IR spectra of an unknown substance, it is not possible to know where it is pure compound or a mixture of compound. Because सभी के बैंड आने हैं इधर, जो भी डाइपोल मोमेंट दिखाएगा वो अडल्ट्रेटेड ड्रग रहेगा या फिर आपका API रहेगा. API भी अडल्ट्रेटेड हो सकता है, तो वो मिक्स आपको IR स्पेक्ट्रा दिखाएगा. ओके, सो उससे आपको पता नहीं चलेगा कि ये पैरासिटामोल जो हमने अभी IR स्पेक्ट्रा निकाला है ये प्योर 100% पैरासिटामोल है या फिर अडल्ट्रेटेड है. बिकॉज जो अडल्ट्रेटेड रहेगा उसमें भी कार्बन रहेंगे, उसमें भी नाइट्रोजन रहेगा, उसमें भी ऑक्सीजन रहेगा, उसमें भी बेंजीन रिंग रहेगी, वो भी दिखाएगा. सैंपल सेल्स आर मेड अप ऑफ हाइड्रोजन सॉल्ट्स व्हिच आर ससेप्टेबल टू moisture to tap the moisture. Okay, and gas sample can't be analyzed as the lack of sensitivity. So thank you, that's it. So thank you Manjusha Sanap ma'am, and thank you organizing committee. Thank you Professor Ganeshmal Chaudhary sir. Thank you Dr. Nitin Mohire sir, principal of our college, to give me platform to explain the lecture or to deliver the lecture on faculty development program. Thank you so much. YouTube live stream पे जो भी सुन रहे हैं उनको भी thank you. Thank you.
Thank you so much, ma'am. Now proceed further. I requesting to Professor Manjusha Sanap, ma'am. Please give the vote of thanks for today's session.
Thank you. So today I deliver a vote of thanks for our resource person, Prajakta ma'am. She nicely talked on IR spectroscopy. She explained the theory of IR spectroscopy, various molecular vibrations in depth. She also explained the criteria for a molecule to absorb the IR radiation. She very well explained the instrumentation. Then, as well as she explained the example of various compounds by using IR spectrum. She explaining the factors affecting IR spectrum like Fermi resonance, coupling, overtones in detail, as well as she explained the limitations of IR spectroscopy. Prajakta ma'am delivered a very informative and in-depth session on IR spectroscopy with her good knowledge on IR spectroscopy. So I am very thankful for Prajakta ma'am. So deliver a nice session. Now I introduce our next resource person, Dr. Lalit Sonone sir. First, I welcome Dr. Lalit Sonone sir for this fifth day session second on this online faculty development program on exploring the spectroscopic and chromatographic techniques in pharmaceuticals. Dr. Lalit Sonone sir, he is a very versatile healthcare professional with extensive experience of 13 years experience in research and pharma industry. With his strong qualities like strong communication, prioritization, organizational, and time management skill, he achieved various higher positions in various industries. Currently, sir working as a manager in PPD Pharmaceutical Development Department at Thermo Fisher Company, Mumbai. Earlier, sir worked as a project manager in clinical operations as Raptim Research Private Limited, Mumbai, where he handled various responsibilities like planning, implementation, and tracking of clinical trial activities. Sir visited to sir given a site visit to smooth conduct of clinical trial activities. Sir also worked in Synergon Private Limited, Bangalore as a manager in clinical operation from June 2021 to January 22. Before that, he worked in Micro Lab Limited, Bangalore as an assistant manager in clinical research. Sir also has the experience of research coordinator from 2022 to 2018 from Maharashtra College of Pharmacy, Nilanga, Indira College of Pharmacy, Pune, and Rajaram Bapu College of Pharmacy, Kasegaon. Sir completed his B.Pharm from North Maharashtra University, Jalgaon in 2004, M.Pharm from Shivaji University, Kolhapur, and PhD from North Maharashtra University, Jalgaon. Sir has published 22 research papers in various national and international journals. Sir published 4 patents, or sir awarded by 4 patents. Sir, he is the author of 2 books, Pharmaceutical Chemistry of Natural Products by Career Publication, and other book is Practical Handbook of Pharmaceutical Analysis by Nirali Prakashan. Sir is a reviewer of more than 10 international journals. Many more to say about this, sir, because the biodata is very long. So many more to say about this, sir. So we are very fortunate to have such a great resource person among us. So now I request Dr. Lalit Sonone, sir, to continue his session. Thank you, sir.
Yeah, hi, good morning. Am I audible? You please confirm.
Yes, sir.
Okay, loud and clear, right? Because I have joined through my mobile and I'm using headphones, so it will help me. Yeah, so thanks, Professor Manjusha, for such a nice introduction, and many more thanks to my friend, Principal Dr. Nitin Moire, for giving me an opportunity to interact, rather share my experience with colleagues from academia across the state and nation. So, may I request Professor Manjusha to share the presentation to begin with? Hello.
Yes, sir.
Could you please share the presentation what I have shared?
Wait, sir, wait.
Yeah.
Yes, we open, sir. Wait for 2 minutes.
Okay.
Yes, sir. We share.
Yeah, perfect. Am I audible?
Yes, sir. Yes.
Yes, sir. Yes, sir.
Yeah. So we'll be starting with the mass spectroscopy. So currently, I'm working as a manager with PPD Pharmaceutical Development based at Mumbai, which is a part of Thermo company from USA. Yeah. Next slide, please. So I'll not go much deep on the definition and whatever you are getting through, textbooks as well. So this definition per se, it is a technique by which we can, know the composition of sample on a molecular level and the components of the structure of the compound. And these particularly mass spectroscopy is widely used, for the determination of molecular weight, which is based on the molecular M by E, that is the molecule to energy ratio, and the large compounds like peptides, proteins, or those are having branched amino acid chains involved into it. So basically, the mass spectroscopy is used for the determination of the chemical structure or molecular weight for the large compounds, for which none of the other sophisticated analytical techniques could give better information about the large molecules. So the mass spectroscopy has been described as the smallest scale in the world, not because of the spectrometer size, but because of the size of what it weighs. So a molecule with a molecular weight of 1 Dalton unit can also be, determined with the help of mass spectroscopy. So it is, the world's smartest and smallest scale, which can measure the molecular weight of any compound with a lesser and lesser molecular weight. So it is, one of the best tool available for determining the molecular weight as well as chemical composition of any kind of compound, whether it is from natural sources, whether it is from synthetic source, whether it is from semi-synthetic source, or whether it is an biological product. So because of the smartness of this instrumental technique, we can measure the molecular weight and the chemical composition or structure of that chemical entity. Next slide, please. So, see, this is the basically history about how the molecular spectroscopy got developed over a period of time. So, when it has started in, let us say, late 90s, like 1897, where early mass spectrometry has been, theoretically presented in one of the conferences, wherein the scientist has presented that we can determine the molecular weight as well as chemical structure for any of the compound which is present into the laboratory. In early 20s, like 1990, the observation of isotopes using mass spectroscopy has came as an revolution into the industry or into the science per se, wherein we are determining the structure. So, for isotopic measurements, like let us say we have 13C as an isotope of the carbon, or we have O17 as an isotope, or you would have seen the isotopes for iodine, bromine, chlorine, for uh, you know uh, any kind of molecule. There are some isotopes with +1 charge. So these isotopes were determined by using the mass spectroscopy. But before that, the isotopes were not separated out. Then in 1934, focusing analyzer. Then 1939, AMS, that is accelerator mass spectroscopy. In 1946, the TOF mass spectroscopy, that is the time of flight. For how much time the molecules or atoms are flying into the air or into the analyzer of the mass spectroscopy. So based on that, those ions will get separated out, and it will come as an output through the detector into the mass spectroscopy. So TOF is the most widely used mass spectroscopy tool, which is being used since long time. It's almost more than 50-60 years. Then preparative mass spectroscopy, ion cyclotron resonance, that is ICR, then reverse geometry, double focusing, and quadruple analyzer. So these are the evolutions which took place over a period of time. But as of now, time of flight is the best, what we can say, method, which is determining the exact molecular weight based upon the time of flight of that particular ion into the detector system. Next slide, please. Yeah, next slide. So yeah, so over a period of time, there were many research going on mass spectroscopy, how it can be clubbed or hyphenated with some of other sophisticated analytical techniques. Like it has been clubbed or hyphenated with gas chromatography, from where the compounds are getting separated through chromatography, and they are directly getting injected into the mass spectrometer, and from there it is getting fragmented into the ions and giving us the exact molecular weight as well as chemical structure of every separated chemical entity. Then over a period of time from 1962, 1966, then 1968, a few of the imaging methods, few of the ionization methods which were completely new to the world were given by different scientists. Then the field desorption method came into picture in 1969. That is whether it is MALDI, that is matrix assisted laser desorption technique, or it can be a matrix MALDI is the matrix assisted desorption technique, and SALDI, some are the surface assisted laser desorption techniques which are used for the ionization. So in coming slides, which we are going to see what exactly happens into the MALDI as well as SALDI, and how the ions are getting separated based on their time of flight. So as of now, even in industry, we are using the matrix assisted laser desorption ionization technique along with the TOF analyzer, that is time of flight. So it is, eventually the mass spectroscopy has become multi-TOF mass spectroscopy, and more advanced is the multi-TOF. So for complex compounds wherein the molecular weight or the chemical structure is almost one and the same, and there is only an addition of one hydrogen or one methyl group, which tends to increase the molecular weight, or there are changes into the chemical structure. So just to have a refinement into the analyzing technique, the time of flight has been added as an integral part of the mass spectroscopy. So for that, it is called as multi-top. So you have better resolution into the spectra, which you are getting as an output through the detector. Okay, so you can better judge the molecular structure or the molecular weight for that particular complex compound. Next slide, please. Yeah, so after that, we have few, no, oh, sorry. So after that, we have certain techniques like electrospray ionization for biomolecules, wherein the biological molecule is getting bombarded with certain electrons, and then uh, it helps in monitoring the enzyme reactions, and the most complex structures like the proteins or some non-covalent interaction with electrospray ionizations, and the clinical mass spectrometry came as an advanced technique over a period of time. Can I have next slide? Yeah, so these are again a few of the techniques which came in, as a gift package of the mass spectroscopy to the world. And these things, you can get through the books as well. Next slide. Yeah, so this is what is more important when we are, looking at the mass spectroscopy as an advanced, sophisticated analytical instrument. So, what information can be determined with the help of mass spectroscopy? So, but obvious molecular weight is the prime, area or the determination which we can have with the mass spectroscopy. Then molecular formula, like high resolution molecular spectroscopy, can be used for the determination or elucidation of the structure of the compound or molecular formula for the compound. So there is N13 rule, which we can apply as a logic, and we can determine the molecular formula for any unknown compound. Then isotopic incorporation or distribution of the compound, and protein sequencing with the help of hyphenated technique like mass spectroscopy, again hyphenated with mass or coupled with one more mass, wherein you can determine the molecular sequence or the protein sequence present at the receptor structure. Next slide. Yeah, so this is the block diagram for a generic mass spectrometer. Generic, it means that there are no hyphenated techniques involved, or it is not been clubbed with or attached to any of the other sophisticated analytical technique. Like this is a very simple block diagram what we can see in book as well. So there are some ionization source from wherein once the sample is getting injected into the mass spectrometer, it will be bombarded with some ionization sources. So it can be, what we can say, it can be bombarded with some gases, it can be bombarded with some of the electrons or some magnetic field. That is how the molecule is getting fragmented or broken down into individual ions, and once it is getting broken down into the or it is present at ionized state, it will go into the mass analyzer, and because of some certain whether it is an electric field or magnetic field, those fragments or ions will get distributed based upon their molecular weight, and post that it will go to the detector system where based on their time of flight. Let us say if hydrogen molecule is there, so hydrogen is having a molecular weight of only 1 Dalton unit. So for 1 Dalton unit, it may not flight for long time. Okay, and it will get settled down onto the detector system, and your output will give you as 1 Dalton unit. M by E ratio with a particular intensity that will correspond to 1. So that automatically gives you an information that the particular compound is having hydrogen into it. This is just for example. And then if you have nitrogen, then for nitrogen, the molecular weight is 14. For oxygen, the molecular weight is 16. For carbon, the molecular weight is 12. So based upon their molecular weight or M by E ratio, those fragments will get separated out. They will settle down onto the detector based upon for how much time they are there into the time of flight, for how much time they are flying into the vacuum and then getting settled onto the detector. So based on that, the output will get generated. Can I have next slide? Yeah, so these are certain or ionization techniques or sources for ionizing the molecule, like electron ionization, chemical ionization, photo ionization, ESI, then matrix assisted laser desorption, field desorption, plasma, fast atom or high temperature uh, plasma. So these are the inert gases which are getting injected along with the sample will ionize that particular compound into different fragments or ions, and post that it will go into the mass analyzer. So information about all these ionization techniques and what are the gases or chemicals which are used for the ionization process. This information you can read out through the books as well. So I'll be talking something about the molding, which is matrix assisted laser desorption technique, wherein a particular compound, unknown compound, will be stick to or bound to a particular matrix, which will be an inert matrix, and on that inert matrix, the laser beam, okay, laser rays get bombarded onto that, and because of certain changes into the energy of the molecule, the compound will get ionized into different fragments. So that is how basically the matrix assisted laser desorption techniques takes place. And there is one more which is known as surface assisted, that is SALDI. So in SALDI, the unknown compound or compound of our interest will get bound to or stick to the surface of a particular, let us say, inert material, and then the lasers will be bombarded onto it, which will help in ionizing the unknown compound into different fragments. So that is how the MALDI and SALDI takes place as an ionization source for the mass spectroscopy. Next slide, please. Yeah, so I'll not talk much about, because I want to cover the applicability of the mass spectroscopy in industry as well as in not just only industry but academia as well as the research also. So basically in electron ionization technique, This particular is used to produce gaseous ions for analysis. So as we know, the TOF, that is time of flight, is best suitable, and there are certain inert gases like helium, nitrogen, which are used as a carrier for those electrons which are getting transferred to the mass analyzer, and after that it will go to the detector system. So these are used as an ionization source. Next slide, please. Hello. Yeah, can I have next slide? Next. Yeah, so the previous slide, please. Yeah, so how the electron ionization takes place. So this figure will show you how the electron beam is provided onto the compound, and based upon the charges of the molecules or the components which are present into the chemical structure, based upon the charges, those are getting separated, whether positively charged ions or uh, negatively charged ions. So those will get attracted towards the cathode or anode, or they will be there onto the filament. So electrons are emitted from a filament mode of tungsten or rhenium. So tungsten as well as rhenium, these are the two materials which are used, to get the electrons which will get bombarded onto the unknown compound, and those are accelerated by a potential of 70 volt. The electrons and molecules cross usually at a right angle and collide on each other, and the primary ions are primarily singly charged positive ions that are extracted by a small potential through a slit. So slit is something which is present in between the ionizer and the mass analyzer. So through that slit, the singly charged ions will get flown away by providing some kind of potential or current. Next slide, please. And when the electron hit, the molecules undergo a low vibrational excitation. That is, the mass of electron is too small to really move the molecule. And since the charges which are present onto the electrons are less, we are using electrons which are there, or sometimes the gases which are there, which will move the compound or electrons to the mass analyzer. So about 1 in a million molecules undergo the reaction, like M plus E, that is electron, which will give you the fragmented molecule or fragments as M plus plus 2 electrons. Next slide, please. So advantages, it result in complex mass spectra with fragment times useful for structural identification. But the disadvantage is it can produce too much fragmentations, leading to no molecular ions. So whatever reaction we have seen, wherein we are getting M plus as the one fragment of a particular compound with additional charge onto it as plus. So the main disadvantage or drawback of this electron ionization or electron impact is that it can produce multiple fragments of a particular electron. Then in chemical ionization, which is a very softer technology, wherein we are using certain gases like methane, isobutane, or ammonia, uh, those are getting introduced at a source of into the source at 1 torr pressure. So let us say if we have CH4 as a reagent gas. So CH4 is again from structure you can see it is having one, it is a methane gas which undergoes the ionization, and it bears one positive charge. So when this methane gas is again interacting with the methane gas, you will have two more fragments. So in chemical ionization also, the number of fragments is getting increased. Because of that, again, it is not much advisable to have the chemical ionization as the source of ionization or source of fragmentation for that particular structure. Next slide. Uh, can you please zoom in? Next slide. Can you zoom it if possible? Yeah. So this is one example wherein we have a particular spectra. Let us say, yeah, enough. I'm okay with that. So here we have a compound whose molecular weight is 157. So when the chemical ionization takes place, you have additional electron present into it, because of which the molecular weight is getting added with one molecule. Like you have a spectra with M+1 as 158. So basically here, if you will see the fragmentation pattern in first figure, you have a peak at 112, which represents the C8 and H16, which is getting fragmented. So if you have a structure with, let us say, CH3, CH2, 8 times, and CH2OH, which is an alcoholic group. So this OH will get fragmented, okay, and you may get a base peak at 41, which represents CH3H5. So how this base peak has come? So for this, we really need to study the fragmentation pattern and the intensity of that particular peak. So for base peak, as it is a thumb rule, any peak which is intensity or relative abundance of 100% will be a base peak always.